조이, 오케이. 김민성, 김혜영, 김수학, 윤동기 없어요? 윤동기 없죠? 황진우, 김윤호, 박찬휘, 설재학, 홍채원, 이혜성, 이동준 없어요?
22학번.
야, 22학번 이동준, 그죠? 최성규, 장지민, 문서영, 문채원, 남희주, 진재범 없어요? 이현규, 홍채은, 김서연, 고건, 이가을, 이도형, 안기범, 조영남, 김기찬, 현지호, 이정재, 김성원, 이은성, 이현, 임석훈, 엄재형, 윤강수, 권하현, 이윤중, 박재빈, 김지호, 안지민, 네. 김태훈, 김재혁 없어요? 하준석, 김지용, 김혜인, 엄석현, 네. 장우진, 박서진, 한재현, 김기석, 남병준 없어요? 엄재정, 이찬민, 양재모, 윤수영, 마르원, 강동언, 석규원, 임기영, 김도엽, 서현석, 구영모, 윤나영, 안가은, 앵드자야, 김소정, 노재현, 이환석, 이성재, 남상우, 홍승표, 이재훈, 윤예담, 허민, 이준원. 오케이? 안 부른 사람 없죠? 수업 시작하도록 하겠습니다. 지난주 수요일 수업은 죄송합니다. 급하게 교수 회의가 엄청 중요한 교수 회의가 잡혀서 조금 short notice로 취소를 하게 됐는데 그런 경우 이제 없을 거예요. 아마 없을 겁니다. lecture 2를 이번 주에 이어서 진행하도록 하겠습니다. structure and bonding 파트를 다 마무리 못했는데 오늘 마무리할 기획입니다. Okay? So we'll keep continuing and finishing the remnant part of chapter 1. So today we'll cover up the remnant part of structure and bonding for organic molecules. Okay? 그 수업을 시작하기 전에 앞서서 요새 나 생각하면 조금 기쁘지만은 않은데 그래도 저희 학부가 최근 발표된 세계 랭킹에서 아주 높은 순위를 획득했습니다. 앞에 학교가 10개밖에 없어요. 제가 알기로는 역대 최대 랭킹을 얻었어요. 11위입니다. 그래서 저희 밑에 있는 학교 보면 EPFL, 칼텍, 프린스턴 다 제치고 저희 학부, 이거 학부 랭킹이에요. 서울대 전체 랭킹은 이번에 한 30위 했나? 20몇 위 했나? 그런데 저희 학부가 아주 강한 학부예요. 그래서 세계 랭킹 케미컬 엔지니어링 디파트먼트에서 11위를 했습니다. 그래서 여러분 자부하셔도 좋고 이제 저희 학부에서 지금 2학년 학생들 대부분 3, 4학년 학생들도 있는데 열심히 공부하시고 학부 이후에 대학원 과정에 많은 관심을 가져주길 바라요. 저희 대학원 랭킹이에요. 결국 11위라는 것이. 그래서 여기보다 더 위에 있는 학교로 유학 가고 싶다 꿈꾸셔도 좋은데 굳이 갈 필요 없다. 계속 올라갈 거고 저희 학부 교수님들은 이제 7, 8위까지 올라가는 걸 목표로 하고 있어요. 그래서 위에 MIT, 버클리, 스탠포드, 버클리는 없나? 버클리 여기 있네. 영국에서 하는 랭킹 조사기 때문에 캠브리지 런던 빼고 나면 저희 10이 아니라고 봐도 무방하죠. 그래서 좀 기쁜 소식도 있다. 그리고 노티스 관련해서 어나운스먼트 관련해서 지난 시간에 저희 midterm final 확정했습니다. 그래서 이제 there will be no more change. So this is a fixed date for exam for midterm and final. Okay? 지난 시간에 우리 다 합의를 받고 시간도 10 a.m. To 12:30 p.m. Okay? So this is a fixed date. So please mark your calendar. There's no more change. The lecture 2 last week got cancelled, so we have changed schedule completely. And today we'll finish the remnant part of chapter 1 actually. This should be chapter 1 and 2. Okay, and I will upload this modified file after this lectures, but basically we have the same materials as I noted last week. So we couldn't finish the Kepler structure, condensed structure, and skeletal structure last time, right? This is a way in which you can present the structure of organic molecules. Be quite handy, useful, save your time. So we'll discuss about that, and then we'll move on to the molecular orbital theory, hybridization theory, which are very useful for describing the bonding nature within the organic molecules. Okay, but which we'll discuss how you can rationalize and explain the bondings within the organic molecules. Okay. 그래서 지난 시간에 저희가 아마 restructure는 다 사실 아시는 내용인데 젠캠에서 다 배우는 내용인데 한번 리뷰를 해보시길 바라고요. 유기화학, 유기 모레큘을 다루는 데 있어서 이제 조금 유용한 structure representation 방법이 있습니다. skeletal structure, condensed structure, Kepler structure가 무엇인지를 간단하게 다루고 주로 많이 이용한 것이 또 skeletal structure예요. 그래서 연습 문제 등등 좀 푸시면서 익숙해지시면 될 것 같고 그 이후에 이제 MO, hybridization theory를 배운 이후에 organic molecule에 등장하는 bonding, typical bonding tendency 혹은 트렌드를 어떻게 설명할 수 있는지 좀 이론적인 거를 간단한 기초적인 거지만 그래도 중요한 내용입니다. 그래서 앞으로 유기화학을 공부하시는 데 있어서 좀 기초가 될 만한 내용이니까 오늘 수업을 듣고 복습을 해주시기 바랍니다. Okay, so these are the range of topics, okay, for today's class. So, what is Kepler structure? So, in this slide we are discussing the difference between Kepler structure and condensed structure. Okay? So, Kepler structure is basically the restructure, but without the lone pair representation. Right? So, in this somewhat simplified version, you don't need to express or notify the location of the lone pair. So we don't have, for instance, lone pair notification in this Kepler structure. Okay? So it's basically same thing, same as the root structure, but you can omit, right, the lone pairs. Okay. And what about condensed structure? As the name refers, right? You can omit some or all covalent bond, but then the molecule, and at least atoms bonded to a particular carbon, right? Or a nitrogen oxygen next to it. So this is example of the condensed structure. So with this notification, you can identify where is the bond exists, right? For instance, for this molecule, you know that there's a bond between carbon and Br. And what about these? This is ether, right? And you can get a sense, right? There's a bond between carbon and central oxygen, and also the central oxygen and this carbon, right? And also for this is formic acid, right? And you know that there's a bond between carbon and hydrogen for this notification. And this is a primary amine, methylamine, and you know that there's a bond between this carbon and nitrogen. And more examples, the Kepler structure versus condensed structure. This is table 1.5, and you know, let's say you have this exemplary molecule, and this is a given Kepler structure for this molecule as well, right? And then you can transfer or translate this Kepler structure into the corresponding condensed structure. And then the right hand side, you have condensed structure, right? And basically the atoms, right, bonded to a carbon are shown to the right. So you can, right, get a sense there's a bond between this carbon and this carbon, right? So atom bonded to a carbon are shown to the right of the carbon, right? So you know there's a bond between carbon and carbon, or connected to a carbon by a line bond above or below the carbon. So this is the bond notification, right? So you know that there's a bond between this carbon and this carbon, the Cl, in this case too. So you can designate or represent the bond with a line above or below the carbon, right? And sometimes you can shorten the repeating unit, right? So this is the condensed structure for this molecule, given as a Kepler structure, right? Now you know that there's a bond between this carbon and this carbon, and this carbon and this carbon, right? Here and there, right? With this notification, and so forth. But you can maybe lump these 4 units into one, right? And then you can notify the repeating number, right? So these entire moieties can be shortened as the CH2 times 4, right? And you need a parenthesis to present the repeating unit. Okay. What about this, right? The groups bonded to a carbon, right? So this methyl moiety, for instance, can be shown in parentheses to the right of the carbon, right? This notify this moieties, right? So with this parenthesis, you can identify there is a bond between this carbon and this carbon, but this is a dangling unit, right? So the bond between this carbon and this methyl unit corresponds to this bond, right? But this carbon still have a bond with this carbon, right? So that bond is here, okay? So this carbon has a bond with this carbon, right? But at the same time, the carbon at the left, right, have the dangling methyl unit, right? What's given here in parentheses, okay? And you can do the same thing for this hydroxyl moiety, hydroxyl group. So you have again here OH in parentheses, meaning this carbon, the carbon left, having this bond, right, with oxygen. But at the same time, this carbon has a bond with this terminal carbon as well, right? So that's how you can read, right, the parentheses, the condensed structure, right? Or as we learned from the top, right, you can apply the same rule. You can use the vertical line, right?
to indicate the bond between this carbon and methyl and this carbon and hydroxyl group, right, respectively. And you can also think about what about the next line, the final line, the single group bonded to the terminal carbon of a chain. For that, you don't need any parentheses, right? So you can just leave it as it is. Okay. So the species or moieties in the middle carbon, right? Not on the terminal carbon. You put the parentheses. Otherwise, at the ended or terminal carbon, and the species attached to that ended carbon or terminal carbon, you don't need the parentheses. 그래서 복잡한 건 없죠, 그죠? 한두 번 연습해 보시면은 아마 감을 잡으실 겁니다. 그래서 문제를 푸시다 보면 condense structure가 주어질 수도 있어요. condense structure로 주어졌을 때 이게 어떤 형태의 본드로 이어져 있는지 여러분이 translation 하실 수 있어야 됩니다. 그래서 이 테이블에서 다루고 있는 룰들을 조금 한번 곱씹어 보시면 아마 금방 감을 잡으실 거예요. More examples. Let's take a look at the first line, two or more identical group on the terminal carbon. You can just lump into one and provide the repeating numbers. So, for instance, in this case, this carbon has two methyl moieties, right? I'm identifying this carbon, right? And you have one methyl and two methyl group actually, right? In this case, you can lump this methyl moieties into one and then just notify the repeating number, in this case 2, okay? Or you can use this vertical line again, so this carbon has two methyl moieties as given in this chemical structure. Okay. Two or more identical group on the first atom on the left can be shown in parentheses to the left of that atoms, right? Same case, maybe you can highlight this carbon, right? Just here. And you have one methyl group here and second methyl group there, right? And that's why you lump one methyl group, which is 2 in this case. And you can make the vertical line as well to highlight, in this case, right? This bond corresponds to the bond between this carbon and this methyl carbon, right? What about the oxygen, right? Oxygen moieties in this carbonyl, for instance, right? In this Kepler structure, can be presented with this condensed structure. The oxygen doubly bonded to a carbon can be presented with this notification. You can just use the same, right? Double bond notification as given in Kepler structure, or you can use O2, in this case CO2 presentation, or COOH notification in condensed structures indicating this carboxylic acid moieties. 그래서 카본과 옥시전이 주어졌을 때, 특별히 카본과 옥시전의 더블 본드가 존재할 때, 그죠? 그 경우에는 Kepler structure에서 주어진 대로 사용하셔도 되고, 아니면 CO2 혹은 COO로 표현을 하셔도 무방하다. Alright, that was about the Kepler structure. It's basically the same thing, right? The Lewis structure, but you don't need to put the lone pair. That was the Kepler structures, and you can translate that into the condensed structure with the rules that we just studied. Last one is the skeletal structure. This is quite useful and handy. These skeletal structures, as name refers, it shows the carbon-carbon bond as a line, right? But do not show the carbons or the hydrogen, right? They're bonded to the carbon. So for instance, you can translate this condensed structure into the given skeletal structure down below, right? So you have 1, 2, 3, 4 carbon, right? So each dot here indicates carbon, right? And the line between dot indicate the bond between carbons, right? Since you have 4 carbon, that means you must have 3 bonds between carbons, right? And there's a bond between carbon and Br here at the terminal position, right? That line also indicates the bond, the single bond between carbon and bromine. Okay? You can translate this ether to the given skeletal structures as well. You have 1, 2 carbon and a single bond between this carbon and oxygen, and one more. What about this one? You can translate, right? You can point it out, this carbon right here and there. Then you have ethyl moiety, and methyl moieties, right? So you have 1, 2, ethyl, and 1 methyl, right? And there's a carbon and oxygen bond, right? Which is given here as a line. Okay. This one you can change into the pentagon, right? What about this one? You can make the hexagon with the double bond notification, which is a pension structure. Okay? That is the skeletal structure, quite intuitive and quite handy. But you need to make sure you count correct numbers of carbon. Right? So dot again indicate carbon, right? And line between dot indicate the bond. 그래서 시험 채점하다 보면 항상 요거 한두 개씩 빼먹는 친구들이 있어요. 항상 잘 세시기 바랍니다. 그래서 카본, 닷, 개수가 딱 맞는지. 요거 때문에 완전히 틀리게 채점은 안 하는데 조금 아쉽게 감점을 받는 친구들이 있습니다. So you guys should make sure the number of carbon you translate into this when you translate the content structure into the skeletal structure. Okay? Right. Convert it to the skeletal structure. Right? 한번 연습해 보시죠. So black is carbon, gray is hydrogen, red is oxygen, blue nitrogen, green chlorine. Okay? 가운데로 내릴 수 있지 않나? 잘 안 보이지 않아요? 이쪽에 있는 선들은? 다음 시간에는 알아보겠습니다. 제 기억에 가운데 게 내려올 수 있었는데. Right, let's try from A first, right? Easy. So again, you guys should make sure the number of carbon, right? 1, 2, 3, 1, 2, 3. What about B? You have 1 metal, right? And there's oxygen, and an ethyl. What about C? You have this carbon dot, right? Carbonyl, this is actually an amide, and you have methyl, and ethyl. Okay. What are D? You have again methyl and nitrogen like this. Okay? Again, you guys should make sure you put the correct number of carbon. Okay? There's 1, 2, 3 carbon and 1 nitrogen. Okay? All right, that was about molecular structure, content structure, and skeletal structures. So please practice with the P sets. Right? Be familiar with the content structure and skeletal structures in particular. 그 content structure는 이제 읽으실 수 있어야겠죠. 주어진 content structure 식이 있을 때 이게 어디와 어디에 bond가 있는 건지 정확하게 정보를 해석하실 수 있어야 되니까 연습을 하셔야 되고 skeletal structure도 마찬가지입니다. 주어진 lead structure든 calculus structure든 content structure든 이것을 skeletal structure로 translate 하실 줄 알아야 되고 반대로 skeletal structure로 주어진 것을 역으로도 해석하실 수 있어야겠죠. 결국에는 뭐 bond가 어디와 어디 사이에 있고 애텀 개수가 정확한지 이런 거 더블 체크해 보시면 될 겁니다. Okay. Right, that was about how we can represent the organic molecules. Then we'll review again. I'm sure you guys all know about the molecular orbital theories, hybridization theories, but let's review and how these theories can be used to describe the bonding nature within the organic molecules. Right, I think this is what we covered in lecture 1. And maybe we can ask why you care about orbital in the first place. And as we discussed in lecture 1, the valence electron, right, is very important. Dictate the nature of chemical bonding within a given molecule. And then this is how H2CO, benzene, O2, CO2, and actin molecules look like, showing you the electron density. So we need to know the atomic orbitals, which have particular size and shape, and this is why we need to know about the structure with the orbitals, right? Because the size and shape matters for the reactivities of a given molecule, and it dictates and presents how they are forming the chemical bonds, right? So we need to know how orbital can be formed and how, in particular, the molecular orbital can be formed. Okay. This is somewhat fundamental stuff, so it's not directly related to what we are studying for the OChem, but this is, maybe you can think about this as a general stuff, right? The electrons have a wave-like properties, right? And you know that maybe you learn all about this in Chem, right? Location of electron in an atom, follow the wave function, and wave function looks like this. There's a radial part, angular part, right? And then you probably hold about the principal quantum number, right? And orbital quantum number and magnetic quantum number, NLN, right? And the wave functions are basically the quantum state dictated by the quantum mechanics. So you heard about the Schrödinger equation. This can be, you can solve the Schrödinger equation for one electron system, basically. 젠캠 때 배웠나요? 다들? 그죠? 들어봤을 거예요. Schrödinger equation, one electron system에 대해서 수식적으로 막 풀고, 그죠? Angular part, radial part 수식적으로 다 풀어서 그 수식 어떻게 유도되는지 아마 원리 정도는 배웠을 거예요. 직접 다 푸는 것까지는 안 해봤더라도, 그죠? 그렇게 복잡한 건 아니고 받아들이셔야 되는 부분도 있고 양자역학이 들어가기 때문에 하여튼 이런 양자역학적인 이유에 의해서 양자역학적인 이유라고 하면 조금 더 구체적으로 말씀드리면 양자역학을 고버닝하는 이퀘이션에 의해서 수식적으로 저희가 해를 구할 수가 있고 그 해에 해당되는 이제 그래프를 그려보면 애토믹 오비탈의 모양을 우리가 이제 알 수가 있는 거예요. 그래서 수학적인 해입니다. 수학적인 해. 이거를 이게 왜 이러냐 원리부터 따지기 시작하면 이제 약간 철학의 문제에 철학적인 문제 이제 다다르게 되는데 일단 받아들이시면 돼요. 그래서 오비탈이 뭐냐라고 부르면 one electron wave function이다가 이제 가장 리그러스한 답변이 되겠습니다. 그래서 wave function 아톰 오비탈 다 이어져 있고 아톰 오비탈을 이제 잘 쌓으면 그게 몰레큘 오비탈이 되겠죠. 그렇죠? 그래서 그런 관계성이 있다 정도를 이해하시면 되겠습니다. Okay? So atomic orbital, the definition of the orbital is the one electron wave function. So you can get a sense, right? The electron has a wave-like properties, right? And there's an equation in quantum mechanics right? It's called Schrödinger equation. You solve the Schrödinger equation, then you can solve the structure of the given atomic orbitals, like s orbital, right? P orbital, d orbital, f orbital. We briefly discussed about, right? The shape of this, right? And then lecture 1, I guess. But you can, if you want, you can solve the exact solution of the Schrödinger equation, the one electron wave function. But if you have two electrons, then you cannot solve. 그렇죠? 일렉트론이 하나만 더 들어가도 사실 완전한 핵을 구하기가 거의 불가능합니다. 그래서 one electron wave function일 때는 핵을 구할 수가 있어요. 수학적으로. 이런 얘기 어디서 한 번씩은 들어보셨을 거예요. 이제 결국 이런 원리로 애토믹 오비탈을 이해하시고 이 애토믹 오비탈을 잘 섞든지 잘 빌드업해서 몰레큘 오비탈을 이제 만드는 디오리가 필요하겠죠. 그렇게 나온 몰레큘 오비탈 디오리 가지고 이제 본드를 저희 기술할 수 있으면 됩니다. Alright, so maybe we can review a little bit more about the orbital theory. Okay, so atomic orbitals, you can think about maybe 1s, 2s, and 2p orbital sets. For the p orbitals, you can consider px, py, and pg orbitals. And orbitals, the definition, again, the rigorous mathematical definition was one electron wave function, but this is qualitative description and definition of the orbitals. Again, the region of the space around nucleus where an electron is most likely to be found. Okay? This is the probability that you can find the electron around the nucleus, right? So this is how 1s orbital looks like, right? And you can think about, right, this is the region where you can identify or find the electron around the nucleus, okay? And this is a 2s orbital. Near perspective, right, this looks probably larger than 1s orbitals, but probably you cannot see the node. Define the node later, but inside there's one node here actually, right? It's a node for 2s orbitals. So 2s orbital, you have one node, and node is a location where the probability for the electron exists becomes 0 or nullified. Okay, and this is a general equation you can refer to. How to count the number of nodes. The total number of nodes can be calculated with this equation n minus 1. Right? So for 1s orbital, if you apply n equals 1, then you can get a sense, right? You can get the 0 number, right, for the total number of nodes. That's why 1s orbital has no node, right? But 2s orbital has 1. Right? So if you apply 2 to this equation n minus 1, then you can get 1, right? And that's the one node inside. Okay. What about p orbital set? Px, py, and pg orbital. Okay. This is basically how p orbital looks like. If you have px orbitals, then you have the axis on x, right? If you have py orbitals, then you have the axis on y. If you have pg orbitals, then you have the center axis on g, okay, direction. And there's additional equation you can refer to, the number of radial node, right? So this is a specified node, the radial node, meaning these spheres, right? A fixed distance from the center, which is given as n minus l minus 1, right? And this is the given L number for S, P, D, and F orbitals. If you're dealing with the S orbital, then its L number is 0. If you are dealing with the P orbital, right, then its L number is 1. Okay? So for the organic molecules and organic chemistry we're learning, we're mostly dealing with this S and P orbitals, right? With probably one need to consider D orbital or F orbital for the organic chemistry, organic molecules that we are studying for this course. Okay? But for your information, D orbital, its L number is 2, and F orbital, its L number is 3. Okay, and you can plug in this information to this equation, n minus L minus 1, right? So if we are dealing with the s orbital, that means this L value is 0, right? Then the number of radial nodes will become n minus 1. Okay? That's why for 1s orbital, you don't have any radial node, but for the 2s orbital, you have 1 radial node. But in this case, right, the angular node, right, we're going to be 0. So maybe we can 그래서 뭐 크게 복잡할 건 없고요, 그죠? 반대면은 여기 1이고 0이네. 네. 저 1s orbital 같은 경우에는 노드가 없다고 그랬죠? radial 노드도 없고 angular 노드도 없고 2s orbital이 되면 이제 radial 노드가 하나 있는 거고 angular 노드는 없는 거죠, 그죠? 2p orbital이 되면 어떻게 되는 거죠? 일단 n이 2잖아요, 그죠? 그건 total number of node는 1이 된다는 걸 알고 있어. 그러니까 이 경우에는 이제 요거 두 개 합하면 1이 돼야 되는데 지금 p 오비탈의 L 넘버가 얼마죠? 1이잖아요, 1. 그죠? 그러면은 angular 넘버가 1이고 radial 넘버는 0이 되겠죠. 그죠? 뭐 이렇게 적용을 해서 노드가 일단 앞에 principal quantum 넘버가 얼마냐? 그래서 1 빼면은 total 노드가 되는 거고, 그리고 오비탈의 성격에 따라서 angular quantum 넘버가 얼마냐에 따라서 radial 노드가 얼마고, 그죠? 그러면 그만큼 빼주면 radial 노드가 얼마인지 알 수 있겠죠, 그죠? 그래서 angular 노드는 어떤 형태로 나타나냐? 3D space presentation에서 이제 plane의 형태로 나타나게 됩니다. 그죠? 반대로 radial 노드는 sphere의 형태로 나타나게 돼 있어요. 그럼 이제 코드니 공부를 해보시면 아마 쉽게 이해하실 텐데, 그래서 px 오비탈 같은 경우는 보면 yg 플레인이 노드로 작용하게 됩니다. py 오비탈 같은 경우는 xg 플레인이 노드로 작용하게 되고요. pg 오비탈 같은 경우는 xy 플레인이 이제 노드로 작용하게 되는 겁니다. Okay. So in the 3D space, right, the radial node looks like a sphere, right? As you can identify here, the 2s orbital, whether the angular node seen as a plane, okay, for the 3D structure, 3D space. So for instance, for px orbitals, you can identify this yg plane as your nodal plane, right? For the py orbitals, you can identify the xg plane as a nodal plane, and for the pg orbital, xy plane as a node. Okay. And there's one more thing for the p orbitals. This part is called lobe, right? And the lobes of p orbital, the atomic orbital have opposite phases. That's why you have different color code, blue and green. For instance, in this notification. Okay. And with this, right, rule or equation, this is, by the way, the result from the Schrödinger equation again. So you can just accept this is the rule for the atomic orbitals. You can draw the picture of these, right, 3s, 4s, and 3p orbitals, and maybe you can identify the number of nodes first, right? Just 2, 3, 2, right? The first place, and then you can identify number of radial node and angular node, right? For each case. S orbital, its L number is 0, so its angular node must be 0. Then radial node must be 2. 4s orbital, its angular node also 0, right? Because its L number is 0, right? Then it must have 3 radial nodes. Okay? So you can maybe get a sense. Okay? It look like this. Okay. What about 3p orbital? It's L number 1, so its radial node must be 1. So maybe you can draw and check the 3p orbital and how this looks like. It must have 1 angular node, right, and 1 radial node. 그래서 한번 아마 뭐 답을 알고 있는 학생도 있겠지만 한번 머릿속으로 상상을 해서 그려보세요. 그러면은 확실하게 개념을 잡게 될 겁니다. 답이 있네. So 3p orbital. This is how 3p orbitals looks like. You have the plane, nodal plane, right, and also the radial node, right. The sphere and plane. These are the radial node and angular node respectively. 그래서 2p 오비탈과 비교했을 때 이제 3p 오비탈이 저렇게 생겼습니다. 사실 젠캠 때 아마 다 배운 내용일 텐데 한번 리뷰를 해보세요. 노드 개수로 접근을 하시면 아마 조금 더 straightforward 할 겁니다. Okay. Alright, that was the brief review about the atomic orbital theory, and then we'll move on to the molecular orbital theories. Right? This is the ultimate goal. Since we're dealing with the molecule, we're not dealing with the atomic stuff, right? We're not dealing with the atoms, we're dealing with the molecules. And although we're getting molecules, they are molecules, so we need the molecular orbital theories. Right? So we can extend basically the concept of the atomic orbitals. The atomic orbital surrounds an atom, molecular orbital surrounds a molecule, right? So basically you can build up the molecular orbitals from the atomic orbitals. And this is all along in the Gen Chem, I guess. The covalent bonds emerge when AOs, the atomic orbitals, combine to form the molecular orbitals, right? So for instance, you have this 1s atomic orbital for the hydrogen, right? And you can build up from these 2 atomic orbitals, create the molecular orbitals. Right? So this is the representation showing the overlap of the s orbitals and formulating this sigma bond between 2 atoms, right? And the sigma bond is symmetrical, cylindrically symmetrical. Right? A little bit more details about molecular orbital and molecular orbital theory. The M1 theory states that the electron disputed within the whole molecule, and this is an example of the hydrogen molecule, the H2, the dihydrogen molecule, which has the sigma bond between 2 hydrogen, which is again this cylindrically symmetrical. Okay? And the bottom below showing you the energetics. As this 2 hydrogen make a covalent bond or bond between the atom, right, the energetics change, and this is you can think about the x-axis as the internuclear distance, right? So from right, your 2 hydrogens approaching to each other and formulating a bond, right? Partial bond and full covalent bond, right? So in the middle, the atomic orbitals are overlapping. In the left, the atomic orbitals have a combined, right, to formulate the molecular orbital, right? And this is a bond molecular orbital. We'll discuss the anti-bonding molecular orbital in a later slide. But at this limit, right, in this limit, right, you have the bond length of 0.74 angstrom, and we're at your molecule is most happier in happiest position, right, stable. And from 0 to this bottom, you can measure bond dissociation energy, BDE. So you need this much of energy to break the bond between these 2 hydrogen. That's what the bond dissociation energy means. Or you can think about this as energy gain you can get when you make a covalent bond from 2 atoms, 2 hydrogens. So BDE is a measure of bond strength. So larger the BDE, larger the number, stable or stable the bond is, and then maybe stable the molecule is as well. Mathematically, MOs can be treated as a combination, the linear combination in particular, of a given AOs. So you probably heard about the LCAO, stands for the linear combination of AOs, right? The basic rule for this linear combination is that the orbitals, the number of orbitals are conserved. So the number of molecular orbitals you're creating must be same as the number of the atomic orbitals you combine. Okay, so input and output, their numbers should be same. Okay, so AOs are wave function. So as you learn about the wave, right? You can think about the constructive or destructive interaction between two waves, right? So same analogy can work for the linear combination of AOs. Okay, so you have this two independent atomic orbital, the 1s orbital, and when these two combine, and since the input numbers are 2, right? So MO must be 2. The number of MO must be 2. So one is the single bonding MO, and the second must be the anti-bonding MO. And this comes from the constructive interaction between these two orbitals, right? And this from the destructive interaction between two waves, right? That's why you have nodal plane here, right? Larger the number of nodes, unstable, more unstable the MO is, right? So in this case, you don't have any node, right? 0 node. For this one, this sigma anti-bonding MO, you have 1 node, right? Again, this is from the destructive combination of two waves, two atomic orbitals, and the sigma bonding orbital comes from the constructive interaction or combination of two waves, two atomic orbitals. 별로 복잡한 거 없죠, 그죠? 다 배우신 건데 한번 개념적으로 리뷰를 하고 있는 겁니다. Okay. Right. So quite intuitively, right? The bonding MO has to be more stable. Okay, has less number of node, in this case 0 number of node, right? And this bonding MO basically is C-spin bonding, and this is why actually bonding between two hydrogen, two 1s orbitals can be formulated, right? So you have the one electron here and there, and these occupying this molecular orbitals. And then we'll discuss the number of bond in a later slide with the equation. But basically, this two electron occupying the bonding MO create or give rise to a single bond between these two atoms, okay? and the molecule. Yeah, so anti-bonding MO is unstable, more unstable than the initial atomic orbital energetics. And then once you occupy the electron here, right, the anti-bonding orbital, you are basically detract from bonding. So you are losing the bonding number or bonding order if you put the electron there. Yeah, here's the equation. Bond order, BO, can be calculated. It's the number of electron in bonding MO minus number of electron in anti-bonding molecular orbital, right? And if you make the half of that, then you can get the bonding order. 다 젠캠 때 배운 내용이죠, 그죠? bonding MO에 들어가 있는 일렉트론의 개수가 본드 오더에 중요하고, 거기서부터 anti-bonding에 들어가 있는 일렉트론 개수 뺀 다음에 반으로 나눠주면 본드 오더가 되는 거죠, 그렇죠? 이 경우에는 2개 빼기 0 나누기 2 하면 본드 오더가 1 나오는 거니까 다이하이드로젠 모레큘 본드 오더가 1인 거죠, 그렇죠? Right, that was the simplest case. The MOs created from two 1s orbitals. What about the 2p orbitals? Maybe you guys can try to solve, right? Fill in the middle. 한번 복잡하진 않지만 리뷰 해보시죠. Right, so for the bonding MO, you can think about the constructive interaction, right, between two AOs, and for the anti-bonding orbitals, the molecular orbitals, the destructive interaction should be applied, right? So there's an answer, but these directionality given, right? And once the constructive interaction we made from these two p orbitals, then you can get a sense, right? There's a constructive interaction between this blue and blue lobes, right? Which will eventually create two nodes. Whereas for the anti-bonding MO, right, then you can create these three nodes. Right? So there is a destructive interaction between, right, the lobe in the right hand side and lobe here in the left hand side, right, to create the additional node in between, right. So eventually we'll have larger number of nodes for the anti-bonding orbital. That's why that's located in the above. Then each AO's its energetics, whereas this sigma bonding MO reside below the energetics of the given atomic orbitals. So practically you can make sum. You can think about make sum of the wave, the atomic orbitals, after making one inverted in phase. Right? So for instance, you can make this inverted right in phase and make the sum of this in the left hand side. Then you can rationalize how this can be created. Right? But for the constructive interaction, you can just make sum that's given here. And also you should remember the number of orbitals should be conserved. The number of output should be same as number of input. Okay? So if you're adding 2 to create MOs, then there must be 2 MOs created by the linear combination of AOs. Okay? So this is one case of interaction between p orbitals. The sigma bonds, the p orbitals can create sigma bonds, right? And this is called end-on overlap. Right? But p orbitals can have the side-to-side overlap as well. So this is the case where 2 p orbitals sitting perpendicular to the plane. You can think about there's a plane here, and there's an interaction. There's an interaction this p orbital set can make, and you can again think about the constructive interaction between these 2 p orbitals, and this lobe and this lobe have the same phase, same colors. So you can think about there's a bond between these lobes, right? But in this case, you will have one nodal plane. Okay? You can also create the anti-bonding orbital. This is the pi anti-bonding orbital, and then you can make the phase of this lobe inverted and make sum of that with the left. Then you can rationalize why there's a additional node, one more nodal plane created from this linear combination. Right? So you have more nodal plane than below. That's why you have higher energies for the pi anti-bonding orbital. Okay? So the bottom one is the pi bonding molecular orbital, and the above one is the pi anti-bonding molecular orbital. Okay? And here's a note: the pi bond is weaker than sigma bond. Okay, so it's compared to this sigma bond, right? This pi bond has a weaker interaction. Right? This is because the magnitude overlap is smaller in this case, side to side, compared to the end-on type interaction. So p orbital끼리에도 sigma bond interaction, sigma bond 를 형성할 수 있고, 그렇죠? 파이 본딩을 형성할 수 있고, 그리고 모레큘 오비탈 관점에서 시그마 MO를 만들 수도 있고, 그렇죠? 파이 MO를 만들 수 있다. 그리고 각각에 대해서 엔탈 본딩 MO가 존재하는 것이죠. 그렇죠? Alright, thus far we have discussed the MO with identical entities, right? Left and right, or exactly same, right? So it's exactly same p orbital set. Right? And exactly same 1s orbital, right? What about the asymmetric case? Right? You can also make ML with different electronegativity, for instance, right? So you have p orbitals of oxygen on the right, and p orbital carbon in the left. Right? Because oxygen has higher electronegativities in general, has more stable in energy. Right? Your nucleus can stabilize the energy of an electron with higher electronegativities in general. Okay? So more electronegative, more stable because of the more electrostatic stabilization. This is the general concept. Right? That's why p orbital of oxygen reside below, lower than the energetics of the carbon, the p orbital. Okay? And you can make an MO with these two asymmetric case too. Right? And this is the result, right? You can make the constructed wave function or wave from these two different p orbitals, right? And you can also create this destructive wave from these two different AOs, right? The p orbitals from carbon and oxygen, right? So for the bonding MO first, you can notify, right, the different size and lobe, right? The oxygen part is bigger compared to the carbon case for the bonding MO, right? This is probably makes sense, right? Because oxygen is more electronegative, so more stable MO tends to have more electron densities oxygen side. That's how they can stabilize more the energetics, right? But you can apply the opposite rule to the anti-bonding orbitals. In this case, the carbon is less electronegative, so having more electron density on the carbon side will make the energetics of this MO more stable. Right? So carbon, the less electronegative, contribute more to the anti-bonding MOs, and the vice versa for the bonding MOs. Okay? 그래서 더 안정한 애토믹 오비탈이 그쪽으로 더 컨트리뷰션이 간 스테이블한 번딩 MO를 만들게 되는 것이고, 엔타이 번딩 MO인 경우에는 반대로 드러나게 됩니다. 그래서 더 불안정한 파트 로브가 상대적으로 더 크게 엔타이 번딩 MO에 발현이 되게 되고, MO 번딩 MO에서는 반대로 나갑니다. 그래서 결과를 보시면 오xygen 쪽이 더 로브가 크죠. 번딩 MO에서는, 엔타이 번딩 MO에서는 반대로 나타납니다. 다 수학적인 결과입니다. LCA를 하게 될 때, 리니어 컨비네이션 하게 될 때, 컨비네이션 되는 그 파티션 정도가 바뀌게 되겠죠. Right, indicate the kind of molecular orbital, sigma star, pi or pi star, the result when atomic orbitals are combined as given with the given directionalities. Okay. So for the A, right, this is side-to-side interactions, so it must be pi, but the phase are inverted, right? So this must be pi star. Okay. What about this? Pi bonding MO, right? In this case, you have end-on type interaction, so this must be sigma and sigma for both cases, but in this case, the phase are inverted. This must be sigma star. In this case, you have same phase. This must be the bonding MO, just sigma. 쉽죠? So thus far, we have seen how individual AOs interact with each other to make bond or anti-bond, okay? Within the framework of the MO theory or AO theory. Okay? And then we can now discuss, right, how this formalism, how this framework can allow us to describe the bond between organic molecule or bond within the organic molecule. Right? That's the goal for this chapter and this section. Right? 그래서 결국에는 이 주어진 MO theory 혹은 뒤에서 hybridization theory도 다루겠지만 이 theory를 통해서 우리가 하고 싶은 거는, 우리가 배우고 싶은 거는 어떻게 주어진 organic molecule의 bond를 저희가 rationalize 할 수 있는지, 그게 중요한 것입니다. And if you think about these molecules, right, this looks maybe not that difficult, not that complex, but it's quite difficult to make, right, the linear combination of all cases, right? Do the rigorously correct linear combination AOs. It's basically very cumbersome, right? You have 5 entities here, 1 carbon, 4 hydrogen, 2 carbon, 4 hydrogen, right? They are not just simply diatomic molecule, right? There are so many atoms, 4, 5, 6, right? This has like 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 6, this is 5, right? So there's a rigorously correct linear combination and all of these constant atoms is basically impossible, right? It's not intuitive. So we need to think about hybrid orbitals, right? Which is quite useful and handy to rationalize and describe and predict the bonding nature between organic molecules, right? That's why the hybridization theory is particularly useful for the organic molecules and organic chemistry. So, 젠캠에서 다 배우신 내용인데, 그죠? 저희 앞에서는 LCAO 컨셉으로 모레큐 오비탈을 빌드업하는 거에 대한 이제 기초 이론을 배웠죠, 그죠? A 두 개 섞어서 번딩 에모 만들고 엔타이 번딩 에모 만들고. 근데 이게 엔티티가 2개 정도일 때는 아주 쉽게 직관적으로 하실 수 있는데 이제 애토믹 오비탈의 개수가 늘어나기 시작하죠. 본딩에 참여하는 원자의 개수가 늘어나고 기하급수적으로 LCAO의 조합을 생각하셔야 되는 가지수가 늘어나게 돼요. 그러면은 이제 뭐 아주 머리가 훌륭하시고 이제 수학적으로 뛰어나시면 이게 가능한데 사실 일반인은 이 모든 조합을 직관적으로 할 수가 없어서 특히 올게닉 케미스트리, 올게닉 모레큘에서 등장하는 케미컬 본드를 기술하는 데 있어서 아주 유스풀하지 않다라고 생각이 들 수 있죠. 그래서 사실 유기 물질을 다룬 데 있어서 조금 더 유스풀하고 straightforward한 이제 방법론이 하이브리다이즈 오비탈이 조금 더 하이브리다이즈 오비탈 디오리가 조금 더 유용하게 됩니다. 상당히 유용합니다, 사실. 그래서 하이브리다이즈 오비탈 디오리가 결국은 뭐 모레큘 오비탈 디오리, LCAO 디오리로부터 시작된 컨셉이지만 이제 보다 더 직관적으로 하이브리다이즈 오비탈을 바로 직접적으로 써서 본드를 저희가 기술하는 법을 이제 다시 한번 리뷰할 거예요. 다 배우신 내용인데 그래도 한번 리뷰를 하고 결국 앞으로 올게닉 모레큘을 유기화학 1, 2에서 디스크라이브 할 때는 이 하이브리다이즈 오비탈 프레임워크에서 많은 것들을 생각하게 될 거예요. 시작 단계. 뭐 LCAO부터 시작하실 수 있으면 더 좋은데 그럴 필요가 사실 없다. 근데 하이브리다이즈 오비탈 디오리가 LCAO에서부터 시작된 건 이제 연관성 있다 정도는 이제 기억을 하시면 되겠죠. 그렇죠? 그래서 유기화학 물질을 디스크라이브하는 데 충분하다. 그래서 아주 리그러스한 LCAO 필요 없고 하이브리다이즈 오비탈 디오리만을 기억해 주시면 되겠다. Okay, so how this single bond can be described with the hybridized theory. Okay? And so we can start with the single bond, okay? And we can think about the sp3 hybridization. 지금 몇 시인가요? 10분 정도 남았으려나? 그러면 5분 남았네요, 그죠? 5분만 더 하고 마무리하죠. Okay? So first we can think about how to describe a single bond, and for which we need to on the sp3 hybridization theory, and the representative molecule we can think about is a methane, and this is the structure of the methane given with these perspective formula, Boolean state model, space filling model. But you need to know, right, what this perspective formula means, right? There's a different line, right, solid line here and there, right? These lines are in the plane, okay, in the plane of slide. Okay? But you have these solid wedge representation. This meaning this bond, right? Bond between carbon and hydrogen is protruding out from the plane. Okay? And this is the hatched wedge. Right? This is the bond between this carbon and hydrogen, and this is bond projecting back, right? From the plane. Right? That's how you can think about this 3D structure of this molecule in your head. Right? This is why this is called the perspective formula. There's a 4 bond between carbon and hydrogen, and it's all equivalent. You have same bond lengths, 1.1 angstrom, and the bond angle between hydrogen, carbon, and hydrogen is all same, 119.5. And this can be presented with this Boolean state model as well. This is a variety of the way you can present the structure of the method. Okay, the space filling model here derives out of desire to represent molecules in a way that reflect the electronic structure and electronic surface. And this is electrostatic potential mapping. as we discussed in the lecture 1, this illustrates charge distribution of the molecule. 그래서 뭐 주어진 분자가 있다. 그런 분자를 저희가 perspective 포뮬러로 그리실 수 있어요. perspective 포뮬러를 그릴 때 결국 3D structure를 그리는 건데 종이에다 그려야 되잖아요. 2D 종이에다가. 그렇기 때문에 저희가 solid line 이외에 solid line은 같은 플레인에 있는 거예요. 종이 위에 동일 평면 위에 있는 거고 이제 3D 위아래 개념을 더해야 되니까 이제 wedge라는 걸 쓰게 되고 또 hedged wedge를 쓰게 됩니다. 밑으로 내려가고 뭐 위로 올라가고 이거를 표현하는 거예요. 직관적이죠, 그죠? solid wedge는 위로 이렇게 올라가는 거를 상상하시면 됩니다. hedged wedge는 밑으로 들어가는 걸 상상하시면 돼요. 그죠? 그러면 자연스럽게 머릿속에서 이제 삼청 구조가 그려지시겠죠. 그죠? 이건 보안 스틱 모델은 뭐 이것을 뭐 애톰은 뭐 번드는 그냥 스틱으로 표현한다. 그것뿐이고요. 스페이스 필링 모델은 이제 일렉트론 오큐페이션 관점에서 이 스페이스에서 얼마만큼의 각각의 애톰들이 오큐파이하고 있는지를 보여주고 있는 건데 크게 아주 많이 쓰이지는 않고 대신 뭐 스테릭 힌더런스라는 것을 저희가 이제 뒤에 챕터에서 배우게 될 때 가끔 사용하게 될 겁니다. 그리고 electrostatic potential은 챕터 lecture 1에서 다뤘지만 charge distribution과 관련된 거. 이것도 이제 뒤에서 조금 electron deficiency 혹은 electron richness를 표현할 때 제가 가끔 쓰게 될 거예요. 그래서 이렇게 네 가지를 이제 분자의 구조를 다루게 될 때 저희가 마주하게 될 거예요. 오케이? 그러면 시간 관계상 여기까지 하고 저희가 다음 시간에 하이브리다이즈 오비탈을 이용해서 티오리를 이용해서 어떻게 본드 디스크라이브 할 수 있는지 마저 마무리하도록 하겠습니다.